What do you do when you have a set of data points but the exact value you need is missing right in the middle? You can't just guess, and you can't always run a new experiment. You have to calculate it. Welcome back to the channel Analytics Hub. Today we are diving into one of the most important tools in engineering mathematics and numerical analysis, which is interpolation. So interpolation is a method of estimating unknown values that fall between non-discrete data points. There are several methods of calculating interpolation based on different textbooks. Some of the methods we are going to learn in this video are linear interpolation, graphical interpolation, and Gregory-Newton interpolation formula, also known as forward finite differences. For linear interpolation, it is used when a linear relationship is assumed. It is the simplest and the most common method. It assumes that the change between two known data points is constant. That is, there is a linear common difference in the x variable and the y variable. Now, it comes with a limitation that it is only highly accurate if the real-world data actually behaves in a straight line. If the true data follows a steep curve, linear interpolation will introduce errors. Now for our example 1, it says, given the data below, find the value of f of 2.5 using linear interpolation, graphical interpolation, and Gregory-Newton formula. So the value givens are this. For our s data point, we have 1, 2, 3, 4, 5, 6, and our f of s, which is also equal to y, is equal to 4, 14, 40, 88, 164, and 274. Now we need to introduce a formula. Using the linear interpolation, the formula goes by s minus s subscript 0, or you can call it s naught, divided by s subscript 1 minus s equals to y minus y subscript 0, or y naught, divided by y subscript 1 minus y. Now let's define the variables. Our s is the target input value you are trying to interpolate, and for our question here it is 2.5. So which means we are trying to get the exact value of 2.5 of y when s is 2.5. Now y is the unknown output value, that is our f of 2.5 you are trying to solve for. Now the s naught and y naught are the known data points immediately before the target value, while the s1 and y1, or let me say s subscript 1 and y subscript 1, are the known data points immediately after the target value. You can decide to rewrite the tabular data point in a vertical format like this. From what I have here, 2.5 is the value we are trying to interpolate for, which lies between 2 and 3, and the unknown output we are trying to solve for, it lies between 14 and 40. So the formula can be written as s minus s subscript 0 divided by s subscript 1 minus s, which is equal to y minus y subscript 0 divided by y subscript 1 minus y. Now s is equal to 2.5, the value we are trying to interpolate for, minus s subscript 0 is the immediate value before the target value. The target value is the 2.5. So the value before 2.5 is what? 2. Now our s1 is the immediate value after the target value, which is 3, minus s, which is 2.5. Now for the left hand side, we have y minus y is unknown, minus y naught is the immediate value before y, which is 14, and divided by y subscript 1 is the immediate value after y, that is 40, minus y. Now 2.5 minus 2 gives us 0.5. 3 minus 2.5 also gives 0.5. For the left hand side, nothing changes, we leave it like that. Y minus 14 remains y minus 14. 40 minus y remains 40 minus y. Now 0.5 divided by 0.5 gives 1. When we cross multiply, we have y minus 14 equals 40 minus y. Now we color items to make y set of formula. Minus y comes to the other side, we have y plus y. Minus 14 also goes to the other side, we have 40 plus 14. Now 2y equals 54. Divide both sides by 2, and we have y equal to 54 divided by 2, which gives 27. So y equal to 27 is the value we get using linear interpolation method. Now for graphical interpolation, This is a visual rather than purely numerical approach. You plot all your known data points on a graph, then you draw a line of best fit or a smooth curve that connects them. To find your unknown value, you simply locate the S value on the horizontal axis, something like this. We have our Y axis and the S axis. So this is where we'll plot our 1, 2, 3, the S data point, and here is where we have the Y data point, which is I think 4, 14, 40. Now let's say we have a curve like this, and we are trying to interpolate for 2.5, which is lying between 2 and 3. So we connect, let's say this is 2.5, we connect it straight to the curve. So anywhere it intercepts, we will now plot it to the y-axis, and that will give us our y value using graphical method. Let me continue. So to find your unknown value, you simply locate the S value on the horizontal axis, draw a line straight up to your curve, and then read your corresponding Y value on the vertical axis. The limitation is that it is subjective and prone to human error based on how precisely the graph is drawn and read. And now this is the graph output. This is what I have as my graph. See? So I plotted the values for Y when S is 1, when S is 2, 3, 4, 5, 6, and it gives this curve. Now at 2.5, when I trace it up to this curve and also trace it to the vertical axis, I have a value of 24 on my Y axis. So that is f of 2.5 is equal to 24 based on graphical method. And lastly, we have Gregory-Newton interpolation formula using forward finite differences. The Gregory-Newton forward formula fits a polynomial curve to the data, allowing for highly accurate estimations of curve data. It relies on building a forward difference table where you calculate the differences between consecutive y values, which can be represented as delta f subscript 0, then the differences between those differences, and we keep getting some successive differences like delta square f of 0, delta cube f subscript 0, and so on. And you keep doing that until you arrive at a constant value. The formula then uses these successive differences starting from the top, which is why it is referred to as forward, of the table to calculate the interpolated value. The Gregory-Newton formula can be written as f subscript p equals to f subscript 0 plus p multiplied by delta f subscript 0 plus open bracket p multiplied by p minus 1 divided by 2 factorial multiplied by delta square f subscript 0 plus open bracket p multiplied by p minus 1 multiplied by p minus 2 divided by 3 factorial multiplied by delta cube f subscript 0, and it keeps adding up in the series. It has a pattern to it and it's kind of similar to Leibniz theorem. Now p is given as s subscript p minus s subscript 0 divided by h, where h is just a constant, like a common difference, which is s1 minus s subscript 1 minus s subscript 0. Now let's define the parameters. Our f subscript p is the unknown value you are trying to calculate, similar to y in the linear interpolation formula. Now s subscript p is the target input value you are trying to interpolate, which is also similar to s in the linear interpolation formula. F subscript 0 is the value of f of s corresponding to the s value above the target input value s of p. This one is also similar to y subscript 0 in the previous formula, and s subscript 0 here is the known data point immediately before the target input value, is similar to s subscript 0 in the linear interpolation formula also. Now p is called the shift factor. This represents how many step sizes the target point is away from the starting point. You get that when we apply it to a formula to a question. And h is just a constant range between successive values of s. Also, you can also call it common differences. Now the delta square, delta cube are forward difference operators, and they represent the differences between consecutive y values in a forward difference table. Now for example 1, we can start by calculating our h, which is the constant range between consecutive s values. It could be 2 minus 1, 3 minus 2, 4 minus 3, 5 minus 4, which eventually gives 1. Now for p is equal to s subscript p minus s subscript 0 divided by h. Our s subscript p is the target input value, which is 2.5, minus s subscript 0 is the value immediately before it, that is 2, divided by the h, which we got 1. Now 2.5 minus 2 divided by 1 equals to 0.5. We proceed by drafting our forward finite table. We have the s data point, the f of s or y data point. Then we can add our forward finite operator. Is that it? Forward difference operators. Okay, so it is a good practice to leave a gap after each entry, the way mine is. Now for the first one, our data f naught, how do we get 10? We do the difference between consecutive values of y. So I have 14 minus 4 gives 10. 40 minus 14 gives 26. You notice how this 26 is sitting right between 40 and 14. So 88 minus 40 gives 48. 164 minus 88 gives 76. We can confirm that together. 164 minus 88, yeah, that is 76. Now 274 minus 164, it gives 110. Now because the data points here are not constant, the values are not the same, so we can proceed to the successive differences, that is data square f naught. Now we do the same thing again. 26 minus 10 gives 16. 48 minus 26 gives 22. 76 minus 48 gives 28. Now 110 minus 76 gives 34. Let's do that. Minus 76. So that is correct, 34. Now we proceed again to the next successive differences, which is 22 minus 16 now gives 6. 28 minus 22 gives 6. 34 minus 28 also gives 6. So since we have a constant value, we can stop here. The next thing is to write out the value we need in our formula. We need our f of 0, we need our data f naught, we need our data square f naught, and our data cube f naught. So how do we get that? Right from this 2.5, our s subscript p, you can just, like the s subscript p, draw a straight line across the f of s data point, then slightly to the last entry this way, like that. So what we have above this line, this 14, it will represent our f naught. What we have above this line here, it will represent our data f naught. This is our data square f naught, and this is our data cube f naught. That's what I have here below. Now let's impute them into the formula. The formula says f subscript p equals to f subscript 0 plus p multiplied by data f subscript 0 plus p multiplied by p minus 1 over 2 factorial multiplied by data square f subscript 0 plus p multiplied by p minus 1 multiplied by p minus 2 divided by 3 factorial multiplied by data cube f of 0. We'll stop there because that's the last successive difference that gave us a constant value. Now let's impute the values. F subscript p is now equal to, our f subscript 0 was what, 14, this is it here, plus p is equal to 0.5 multiplied by p minus 1, no, multiplied by data f subscript 0. Data f subscript 0 is equal to 26, so that's what I have here, plus now to the third time we have p is 0.5 multiplied by p minus 1 is 0.5 minus 1 multiplied by data square f of 0 is what, that is 22, divided by 2 factorial. 2 factorial is just 2 times 1. Now plus to the next term we have p, which is 0.5, p minus 1 is 0.5 minus 1, p minus 2 is 0.5 minus 2, and data cube f of 0 gives 6, divided by 3 factorial is 3 times 2 times 1, that is 6. So when we calculate this, 14, we write 14, 0.5 times 26 is just half of 26, which is 13. Now 0.5 minus 1 gives minus 0.5, multiplied by 0.5 again, that is minus 0.25, multiplied by 22 then gives minus 2.75. So if you do the same thing for the last variable, 6 cancels 6, if you calculate this one too, the last term we have is 0.375. Now when we sum them together, it gives us 24.625. Now, comparing the result of the three methods we have worked on, the linear interpolation f of 2.5 gives us 27. Using the graphical method, it gives us 24. And now using the Gregory-Newton formula, we got 24.625. And we can actually say that the Gregory-Newton formula is the most accurate one. For example 2 says, given the data below, determine the value of f of s at s equal to 5.5 using Gregory-Newton formula. The s data points are 2, 4, 6, 8, 10, and our f of s are 14, 88, 274, 620, and 1174. So we'll be interpolating for a value at 5.5, which is sitting right between 4 and 6, and also 88 and 274, which means it must be greater than 88 and it must be lesser than 274. Now, I started with the forward finite table. So this is the s data point, the f of s data point, and starting with the first differences, that is delta f naught. So we can start by doing 88 minus 14, which gives 74. 274 minus 88, where's the calculator? 274 minus 88 gives 196. Now 620 minus 274, it gives 346. Now finally 1174 minus 620, it gives 554. So that is for delta f naught. We do this, we continue on delta square f naught, that is 186 minus 74, that is 112. Now 346 minus 186, 160, and 554 minus 346, that gives 208. So we don't have a constant value yet, so we repeat the same thing again. That is under delta cube f naught. Then we have 160 minus 112, that is 48, and 208 minus 160, it gives the same value, that is 48 and 48. Now we can stop. Then for our h is the constant range between consecutive values in the s, that is 4 minus 2, 6 minus 4, 8 minus 6, which is equal to 2. Now our p is equal to s subscript p minus s subscript 0 divided by h, that is s subscript p is about 5.5 minus the value above it is our s subscript 0, which is 4, divided by 2h. So 5.5 minus 4 gives 1.5, minus 4, it gives 1.5. Now 1.5 divided by 2 gives 0.75. That's the value for p. Now from this table, now we can actually get our f subscript 0, delta f naught, delta square f naught, and delta cube f naught. Drawing a line across it like this. See, if down is a straight one, then let me withdraw. You draw a straight line at the s of p. Now you curve downward. So what we have here, 88 will be our f naught. What we have here, 186 will be our delta f naught. Now what we have here, 160 will be our delta square f naught, and 48 here is the delta cube f naught. Substitute it into the formula, then we have 88 plus p is 0.75 multiplied by delta f naught, that is 186, plus p multiplied by p minus 1 multiplied by delta square f naught, that is 160, divided by 2 factorial, which is 2, plus is 0.75 multiplied by 0.75 minus 1 multiplied by 0.75 minus 2 multiplied by 48 divided by 3 factorial, which is 3 times 2 times 1. So when we calculate all of these in our calculator, using our calculator, we have 88 for the first term, 139.5 as second term, minus 15 as third term, then 1.875 as the fourth term, the last term here. So the addition of these gives 214.4. You can confirm that on your own. So hence f of 5.5 is equal to 214.4 using Gregory-Newton formula. And lastly, it says determine the value of f of minus 1 using the data given below. Using Gregory-Newton formula, the S data point ranges from -4, -2 up to 8, and the f of s ranges from 54155 up to 1225. We have to know the value we are interpolating, where it lies, like the position it lies in the S data range. So -1 is actually greater than -2, but it is greater than 0. So which means -1 is in between -2 and 0. Now here is our forward difference table. This is the S data point, the f of s data point. Now starting with the data f naught, we do the same thing we have been doing. We find the consecutive difference. We find the difference between the consecutive values of y. That is 55 minus 541. It gives -486. Let's confirm that. 55 minus 541. Yes. Now 1 minus 55 gives -54. -53 minus 1 gives -54. So -155 minus 53. That is minus is what? Plus 53. That is -102. Now 31 minus 115. That is 31 plus 155 rather. That is 186. Now 1225 minus 31 gives 1194. So we continue to data square f naught. That is -54 minus -486. That is -54 plus 486. Wait. That is 432. -54 minus -54. That is -54 plus 54. That gives 0. Now -102 minus -54. That is plus 54. It gives -48. Now 196 minus -102 is also like writing 186 plus 102. That is 288. And then 1194 minus 186, it gives 1008. So we don't have a constant value yet. We repeat the procedure again. 0 minus 432 gives -432. -48 minus 0 gives -48. 288 minus -48 gives 336. 1008 minus 288 gives 720. We don't still have a constant value at data cube f naught. We extend to data 4 f naught. So -48 minus -432 gives 394. Let's confirm that. -48 plus 432. That is 384. Now 336 minus -48. That is 336 plus 48. It gives 394 also. And finally 720 minus 336. It also gives 394. Now we have a constant value at data 4 f naught. So which means our formula will extend to data 4 f naught. Now we also need to get our h. Our h is equal to 2. That is just 4 minus 2. 6 minus 4. 0 minus 2. That is still 2. Now our p is equal to s subscript p minus s of 0 divided by h. So s subscript p is equal to what? -1. The value we are trying to interpolate for, minus s subscript 0 is the value immediately before it, that is -2. So that's why I have -2 also here, divided by our h is equal to 2. So we have -1 plus 2, that is 1, divided by 2 equals to 0.5. Now from our table, let me draw out the values we'll be needing. This is -1. If you draw a straight line across it up to f of s and a slant line downward, so we have this one here as our f of 0. This is our data f of 0, data square f of 0, data cube f of 0, then data 4 f of 0. So we'll substitute that into the formula. We substitute that into the formula. F of p is equal to our f of 0 is equal to what? 55 plus p multiplied by delta f of 0. P is equal to 0.5 multiplied by delta f of 0 is minus 54 plus p multiplied by p minus 1, that is 0.5 multiplied by 0.5 minus 1 divided by 2 factorial, which is 2, multiplied by delta square f of 0 is 0 already. So this particular term here cancels out, plus p is 0.5, p minus 1, this p minus 2 is 0.5 minus 2 divided by 3 factorial is what? 6, multiplied by delta cube f of 0 is minus 48 plus p again multiplied by p minus 1, p minus 2. Now we extend formula to p minus 3 divided by 4 factorial. So which is 4 factorial is 4 times 3, 12, 12 times 2, 24. Yeah, 24 times 1 is still 24. Now our delta 4 f of 0 is what? 394. So when we do this carefully using our calculator, we have 55 minus 27 plus 0 minus 3 minus 15, and let me do that. 55 minus 27 plus 0 minus 3 minus 15, which gives us 10. So f of p is equal to 10. And that brings us to the end of this video. So you can try and attempt this exercise and also practice the examples questions again. Make sure to subscribe and engage on the channel. Bye.